In this problem, moles of reactant and products are given, and also the volume of the container. Calculate K equilibrium, so let's just write the expression first. K equilibrium in terms of concentration could be written as K subscript C, and it's simply product, a gas divided by reactant, another gas, raised to its coefficient 2. Then we simply plug in numbers. Just be careful with definition of concentration, which is moles, 1.6 moles of N2O4 divided by the total volume, 4 decimeter cube, divided by 2 moles of reactant divided by 4 decimeter cube raised to power 2. When you do that, in numerator you get 0.4, denominator you get 0.25, and your final answer is 1.6. That's your K equilibrium. Second set of problem is, then again, you're given concentrations of the reactants and the product. Now the trick is, when you write K equilibrium or Kc, you just have to be careful. This time the product is a pure liquid, sulfuric acid. You will not include it. Instead we write 1. That's the only difference. In the denominator, I have sulfur trioxide and steam, H2O. Then we plug in numbers, so 1 divided by, concentration of sulfur trioxide is 0.4. Concentration of H2O, steam, is 0.48. And concentration of sulfuric acid is not needed. So it's just an extra piece of information. So not needed. Do not use it. It's a pure liquid. Its concentration stays as is. So when you do this ratio, it's 5.20. And that's your K equilibrium. Another problem, K equilibrium this time is given, reaction is given, concentrations of 2 of the species is given, the last one is missing, which is oxygen. So K equilibrium is 798. It's still product, which is SO3 raised to power 2, its coefficient, divided by SO2 squared, multiplied by oxygen at equilibrium. So let's just carry it through. 798 equals, sulfur trioxide is 11 mole per decimeter cube. So 11 squared divided by concentration of sulfur dioxide is 4.2 squared. Concentration of oxygen is missing, and that's what we are trying to find. So what you can do is just swap as a cross multiply. So this is 11 squared divided by 4.20 squared divided by 798. And when you do this, you will get concentration of oxygen to be 0.00860 mole per decimeter cube. So that's your answer. In the next problem, you might not be able to read the question. You have sulfur trioxide giving you sulfur dioxide and oxygen. 4 moles of sulfur dioxide and 5 moles of oxygen are present in 2 decimeter cube container. At equilibrium, calculate equilibrium concentration of SO3 and the number of moles of SO3 present. Similar to the problem you did before, except one extra step. How many moles would you have? So I write the equation one more time. SO3, gaseous, equilibrium established, gives you sulfur dioxide plus oxygen, gas. K equilibrium is given to me. It is 1.47 times 10 to minus 3 is equal to concentration of sulfur dioxide squared. So let's just find that. Sulfur dioxide squared is 5 moles divided in 2 decimeter cube container. Sorry, 4 moles. So it's 4 divided by 2 squared times concentration of oxygen is 5 moles in 2 decimeter cube. So 5 divided by 2 divided by concentration of sulfur trioxide, which we don't have, squared at equilibrium. So I cross multiply, and I will say concentration of sulfur trioxide at equilibrium is simply square root of 4 divided by 2 squared times 5 divided by 2 divided by your K equilibrium under the square root, 1.47 times 10 to minus 3. And when you do this, you will get 82.5 moles per decimeter cube. So that's part of your answer. Now the second part of the question is, how many moles do I have? Remember, concentration is moles divided by volume of the solution. Therefore, moles is simply concentration times volume. In this case, it's 82.5 mole per decimeter cube times volume, which is 2 decimeter cube. That container is 2 decimeter cube. When you do this, you will get twice as much, so it's 165 moles of your missing species, which was sulfur trioxide. The next problem is you have all the species, their moles are given, the volume is given, and simply it asks you to calculate the K equilibrium. So let's just write K equilibrium and plug in numbers. So K equilibrium is simply products, which they are both gases, so carbon dioxide multiplied by hydrogen gas divided by the reactant. Then again, they are also gases. There is no coefficient, so their exponents, all of them, is 1. Then we simply plug in numbers. So for CO2, I have 4 moles divided by 8 decimeter cube, so it's 4 divided by 8 multiplied by, for hydrogen, I also have 4 moles in the same container, so 8 divided by, for carbon monoxide, 1.6 moles divided by 8 decimeter cube. Finally, for H2O steam is 1.6 divided by 8. Now really, the denominators, all the 8's cancel each other out. So what you have is 4 times 4, which is 16, divided by 1.6 squared. And this will give you the answer 6.25. And that's your K equilibrium. The next question, now we are about to walk into ice calculation. Initially, once you see this word, then you have to really go after a table. Initially, a mixture of 0.1 mole per decimeter cube nitrogen monoxide, 0.05 mole per decimeter cube hydrogen, 0.1 mole per decimeter cube H2O is reaching equilibrium. There is no nitrogen. At equilibrium, concentration of nitrogen monoxide is given. Determine K equilibrium. So I for initial, let me write the equation on top. You have nitrogen monoxide plus hydrogen. They are all gases. They are all involved in the equilibrium. So to begin with, initially nitrogen monoxide, you have 0.1. For hydrogen, you have 0.05. Nitrogen, they tell me there was none, 0, and you have 0.10 mole per decimeter cube of H2O. The next is change, and this time you follow stoichiometry, and from left-hand side you are removing, right-hand side you are producing, so you remove, and you have to respect coefficients. Since you have 2, it's minus 2x moles being removed, and minus 2x moles of hydrogen is also removed, plus x moles of nitrogen comes to life, plus twice as much 2x moles of H2O. What is E? That stands for equilibrium, and it's initial minus change, so it's 0.1 minus 2x. This is 0.05 minus 2x. This is simply x, and this is 0.10 plus 2x. Now they give us another piece of information. They say at equilibrium, concentration of nitrogen monoxide is 0.062, meaning this term is equal to 0.062. So 0.10 minus 2x equals 0.062. Therefore, you can work out what x is. X equals to be 0.1 minus 0.062 divided by 2, and I get I get 0.038. That's my x. If that's the case, then I can also work out what this should be equal to. Is 0.05 minus 2 times 0.038. And when you work it out at equilibrium, this becomes 0.012. X is simply 0.038, so we know the concentration of nitrogen. For H2O is 0.10 plus twice as much, 2 times 0.038. And when you do the calculation, it's 0.162. Now we have all the equilibrium concentrations. Let's just plug in. So it's nitrogen times H2O squared. So it's 0.038 for nitrogen times 0.162 steam squared divided by, now NO, this is the point you shouldn't get confused. There are lots of numbers, but it's 0.062. That's the equilibrium concentration of NO. So 0.062 squared multiplied by equilibrium concentration of hydrogen squared, which is 0.012 squared. And when you work it out, you will get 1801.6. K equilibrium larger than 1, much larger than 1, and you are product favored at this stage. The next problem is also another ice problem. Initial is given. Hopefully there is one information at equilibrium, and then we have to work out K equilibrium. So let me write the equation one more time. Nitrogen plus hydrogen, Haber process, giving ammonia. So I for initial, you have 0.10 of nitrogen, you have 0.10 of hydrogen. There is no ammonia, so that's 0. Temperature and pressure are disclaimer, has nothing to do with my information for calculation. Now change stoichiometry, minus x moles of nitrogen goes, minus 3x moles of hydrogen should go. That's respecting the coefficients, and 2x of product comes to life. Then there is equilibrium. You have 0.100 minus x, you have 0.100 minus 3x, and you simply have 2x. Now let's see what other information is given. Concentration of ammonia is found to be 0.00664 at equilibrium, so 2x is really equal to 0.0664. Therefore, we can work out what x is from here. X is half as much, 0.0332. Then let's just come here and calculate this. Minus 3 times 0.0332 will be extremely small number. This is 4 times 10 to minus 4. And for this, it's 0.1 minus 0.0332. And this becomes 0.0678. We have all the information. We just have to plug in, and we have to be careful with coefficients. So for ammonia, it's 0.0664. Don't put 0.0332. This was working of finding X. So at equilibrium, it's 0.0664 squared divided by the reactant. For nitrogen, we have also 0.0678 multiplied by hydrogen cubed. So 4 times 10 to minus 4. And this will give you humongous K equilibrium, 1.02 times 10 to power 9. This will say it goes to completion, which of course is not a true pragmatic case, but it's good for just sake of calculations and practice. The next problem is you have ammonium chloride gas that is going to be converted to ammonia and hydrochloric acid. K equilibrium is given. This time they give you initial concentrations only. There is nothing about equilibrium. But they say, okay, if this is the case, where are you going toward? Are you on the product side coming back to reactant, or are you on the reactant side going to toward product? So what you need to calculate is reaction quotient. And reaction quotient is like K equilibrium, except this time your products are at initial stage and reactant also. So you plug in numbers, and then you want to compare it to K equilibrium, which is the same ratio except the concentrations are at equilibrium. And then we are going to say, are you going to go toward product or reactant? So let's just calculate our reaction quotient, Q. So Q in this case is concentration of ammonia is 0.02. Concentration of hydrochloric acid, hydrogen chloride rather, is 0.06 divided by ammonium chloride, which is 0.5. When you do this, you will get 0.0024. Now, and K equilibrium is this. Definitely this is smaller than K equilibrium. So now what you need to do is make this ratio bigger. So what you have to do is numerator, which is the product, has to increase, denominator has to decrease. So you are going toward products. You are trying to give more products in the numerator and decrease your reactant. So at this stage, so if Q is less than K equilibrium, the reaction is shifting or moving towards the product, which is the case. If it was Q was bigger than K equilibrium, then you are really going in reverse direction. You're coming back to reactant. If it happens that Q and K are exactly the same, you are at equilibrium. So once initial concentrations are given and you're being challenged as where you're going, calculate that ratio of Q compared to your K. Finally, on this set of problem solving, I have one problem that I want you to solve it without quadratic way of calculations. So this case is hydrogen sulfate is reacting with H2O, the only liquid in the process. The rest of species are aqueous, to give you hydronium and sulfate. Now initial concentration is given, which is 0.1. The rest are 0. And H2O you can ignore because it's pure liquid. Minus X mole is being removed, so this is your I, this is your C. X moles of hydronium and X moles of sulfate come to life. There is equilibrium, 0.100 minus X, X and X. Now they say, what is concentration of hydronium, which is one of the X's? So we are solving for X. So Ka in this case is 1.32 times 10 to minus 4 at RTP, room temperature and pressure, which is standard condition, is equal to products. I can write it as X times X, which is X squared, divided by 0.11 minus x. You can solve quadratically, but there is no need, and you can make an approximation or an assumption. So assumption, you should always write it. Why do you assume and what do you assume? Since equilibrium dissociation is much smaller than 1, it's a magnitude of -4, you can assume that x is so small that when you subtract it or add it to a number, even 0.1 is simply equal to that number. So the x of the denominator only goes away. Therefore, this is really simplified now. No more quadratic needed. Is equal to x squared divided by 0.1. So I can say what x is, and x is the answer which you're looking for, concentration of hydronium. It's simply square root of 0.1 times this number, which is 1.32 times 10 to minus 5. It moves one decimal place back, and this is 0.00363 mole per decimeter cube. So if Ka is really small, -3 and smaller, you can make this assumption. Good luck. These were typical equilibrium questions in regard to calculations.